But let's start with a nice, comfortable conversation about a subject that I brought up to you already, the conjugates, acid-base conjugate pairs, because it's really beyond the computational part of this chapter, it's the concept. And if you can get this concept right, you can actually logic your way through a lot of these problems, up to the point where then you got to get your calculator out and do something. Okay? So remember that acids and bases, they react with each other. So you really can't have one happening without the other. But if you dump an acid in water, there is no base there for it to react with. But there is. If you put an acid in water, what's the base that it's reacting with?
Water.
Very good. All right. If you dump a base in water, there's no acid there for it to react with. But wait a minute, there is. What is the base? So what's the acid that the base is reacting with? It's water. Yeah, water can be both an acid and a base. And remember, there's a special word for that. And remember what it is? Yeah, very good. You guys are getting all the... I should bring some gold stars with me.
I think you should do.
I keep saying that, but I never do it. Amphoteric. Behaves both as acid and a base. And you can see that in these two examples right here. All right. Here's water acting as an acid when we put some ammonia in water, and here's water acting as a base when we put some nitrous acid in the water. Okay, so let's focus then on just one of these. Let's look at the acid. I'll just use the generic naming, HA, because as we're defining an acid, it's donating a proton to solution. So the proton is the hydrogen, and then the A is everything else. So that when that proton is donated to solution, then what's left over is A minus. That's the everything else. That's the conjugate base of the acid. And the base, water, all right, that means we have a conjugate acid of the base. Now, a base, by definition, accepts a proton from solution. Well, we have H2O, so when it accepts a proton from solution, that's the reaction I told you about that forms the hydronium ion. So the hydronium ion is a base. It's the conjugate, it's an acid. It's the conjugate acid of water when water is behaving as a base. If we look down here, right, our generic term for a base would be B, because it's going to accept a proton from the solution. And when it does, it forms the conjugate acid, which is going to be whatever that base was. Then you accept that proton from solution, then BH is positively charged. If we instead call our generic base B minus, then when it picks up a proton from solution, it becomes BH, and now it's neutral. Because the hydrogen that it's picking up, it's a hydrogen ion, H+. All right? And then the conjugate base of water, when water is acting like an acid, the conjugate base is going to be the hydroxide ion. So the hydroxide ion acts as a base. The hydronium ion acts as an acid. And you can see that on this scale. You can see on the left-hand side, all right, we have strong acids as they're getting weaker and weaker and weaker and weaker until we get to this part here that says very weak base. I'm going to relabel that for you. We're going to call this negligible. So those are acids on the left, and we have bases on the right, starting with really, really strong bases at the bottom, working our way up. And as we go up, we're getting weaker and weaker and weaker until we get to the very weak bases, and these are going to be also negligible. Now, what do I mean by negligible? But first, let me just emphasize the pairing here, all right? These are all conjugate pairings. So, for example, NH3, right? Here's ammonia, and the conjugate acid of ammonia is the ammonium polyatomic ion. So if you look for that here on the table, all right, here they are. They are a conjugate pair. If we look at nitrous acid, okay, listed as their conjugate pairs. And I'll just remind you, what do we mean by negligible and strong? Well, you know strong and weak. We talked about that. What's the difference between strong and weak? Right? Strong dissociates 100% or virtually 100%. Weak dissociates less than 100%. So negligible means that it hardly dissociates at all. Right? It's of negligible strength. It might be a little tiny bit, but it won't factor in. Okay? So let's just remind ourselves when it's strong, and let's use HCl here as an example. When we take a strong acid like hydrochloric acid, it dissociates virtually 100% into hydrogen ions, which are really hydronium ions, plus chloride ions. And then we identified that here on the table, all right, chlorine as an ion is the conjugate base. But it's a conjugate base of negligible strength. If it's strong, it goes virtually 100% to products. And you know about equilibrium now, right? It's not going to go in reverse. If we have chloride ions there, it's not going to combine with the hydrogen ions in solution to go back and form HCl. That's what we mean by virtually 100%. That's what we mean by strong. Which is why, as a conjugate base, we can say that it's a base, but it has negligible strength. Okay? And then the opposite's going to be true down at the bottom here. If we have a strong base, and all of these are strong bases. You know sodium hydroxide as a strong base. NaOH goes completely into sodium ions plus hydroxide ions. But it's really the hydroxide ion that's the base. The sodium is just the spectator ion in that reaction, in that whole net ionic equation. So if that's a strong base, so as a base, what's the conjugate acid? Well, it's water. Right? Just as we discovered, right, when water acts as an acid, right here, okay, hydroxide ion is the conjugate base. But again, in this context, it's of negligible strength. Actually, on this table, it's listed just above as a weak acid. Okay. That also means then that everything that's in the weak domain, everything that's a weak acid, has a conjugate base that's also a weak base. Okay? And vice versa. If you have a weak base and you put that into solution, it's going to form a conjugate acid that's also a weak acid. They're both in equilibrium. I know that might seem a little strange. I'm going to flip back here and remind you of some of these definitions. Where's that slide? This one here. The generic acid and the generic base and the equilibrium expressions. So if we have a weak acid, the conjugate base is going to be a weak base. But if we merge these two together, Ka times Kb gives us K sub W. That's what this slide was all about. And showing you that using the same math that you learned in the equilibrium chapter. So ultimately, this may be weak and that may be weak, but together in solution, they're going to come out to be K sub W. That's a constant. And using those same principles of Ka's and how you manipulate them that we learned in the last chapter, we can look at the Ka, for example, the Ka for acetic acid. And that will describe what extent acetic acid will dissociate into hydrogen ion and acetate ions. Or we can look at acetate as a base and calculate its Kb, for that being a weak base, and that's going to be equal to, it's just the reverse reaction. So Ka for acetic acid, which is going to be the Kb for acetate, but that Kb is going to be equal to 1 over the Ka. And this Ka for acetic acid is going to be equal to 1 over the K sub B. Because you learned about that, right? The equilibrium constant for the forward reaction is going to be the inverse equilibrium expression for the reverse reaction. Now I'm going to leave you with that concept for now, and we're going to come back to this a little bit later at the end of this chapter to come back to this same idea of weak acids, weak bases, the conjugates, and how we can figure out what the pH of a solution will be if those are present in solution. All right, but I'm going to leave you till later for that, because that will give us a chance to also review this again as we learn something else with it. So, but let's instead take a look at these weak acids, because there is a whole large sliding scale. Some are weaker than others. Right? Like we consider these to be weak, but they're stronger than these weak ones. Right? There's a sliding scale here. So here's just an example from the textbook looking at 5 different weak acids. And here are the Kas. So you have to remember what Ka is, right? Ka is equal to the concentration of the products, which is hydrogen ion, and the conjugate base, divided by the concentration of the acid. And we don't put water in there because water is a liquid. The concentration of liquid doesn't change. Blah, 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 blah. Right? So take a look at these values. Of these 5 acids, they're all weak acids, but which is the strongest? Which dissociates the most? Are you looking for a higher Ka or a lower Ka for it to dissociate the most? Let me write the reaction to help. Ha is in equilibrium with H plus A minus. So the one that dissociates the most, if we had the same starting concentration. These are all 1 molar concentrations, okay? So if we start with 1 molar of everything, which one will dissociate the most? The one with the highest Ka, because it would be product favored, right? The one that dissociates the most is going to have more products than the others relative to the reactants. So that means the numerator is going to be greater, so you're looking for a larger Ka value. So which one of these is the largest value? You're getting stuck because there's 3 of them that are 10 to the minus 4th, and you're trying to figure out which one it is. Put them into floating decimal, right? This is 0.000177. This is 0.00068. And this is 0.0004. Now can you tell which one is the larger one? Hydrofluoric. So we know that hydrofluoric, HF, is the strongest, followed by, and you just go in sequence. And you can do this easily if you understand what K is and what it represents. So hydrofluoric followed by, what do you think is next here? Nitrous, so that's HNO2, followed by formic, which would be HCOOH, followed by what? Now you can go by the exponents. Acetic, CH3COOH. Lastly, we then have hypochlorous, HClO, or hypochlorous. All right? That's all there is to that. But what if I were to ask you a different question? Let's rank the conjugate bases. From strongest to weakest. Say that louder.
Opposite.
Are you confident? Why is it just the opposite? Why? Why? Because it's the inverse Ka. That's right. Because in this direction, if this is Keq, and in this direction it's 1 over Keq, which of course we're saying this is the Ka, and that's the Kb. So it's going to be just in reverse. And it's the same is true if we go back to this sliding scale. If this is the strongest of the weak acids, then this is the weakest of the weak bases. Right? It's flip-flopping. That's why at the very top we have the strong acids and negligible strength bases. Okay? So yeah, so it's just going to be in the reverse. So let's just write them. I don't need to write them down. Well, let's do it so that you have this, your notes complete. We're going to have hypochlorous is going to be now the strongest base, followed by, actually I need to write these as the conjugates. You learned about naming some of these in Gen Chem 1. Others you're going to learn about how to name them when you take organic chemistry. When you have a carboxylic acid and it's deprotonated, like what we have with formic acid and acetic acid, then it's just the ATE is the suffix. All right, so that's really the concept there, all right? Know how to recognize the conjugate pairs and what to do with that information, and how to interpret. And understand this, that Ka times Kb is equal to K sub W. So as one increases, the other one's going to decrease, and vice versa, because they're always going to multiply out to be the same constant, the ion product constant of water, K sub W. All right, so some of this should look familiar now, all right? The Ka expression, the Kb expression, and strong, when it's strong, all right, it's going to be larger than 1. Pretty much anything larger than 1 we consider to be strong, even though it says really, really larger than 1. Weak ones, they're going to be the ones that go partially. So if we wanted to calculate, so if we had, and I showed you this earlier, but I'll just remind you, we're going to calculate the pH of a 0.1 molar solution. If I gave you a 0.1 molar solution of hydrochloric acid, you know how to solve that one, right? What's the pH of a 0.1 molar concentration of HCl? Who can tell just from looking at that without me explaining it? HCl dissociates 100% into H plus Cl minus. If we start initially with 0.1 molar, 0 and 0, final, all of this dissociates into 0.1 molar and 0.1 molar. So we want the pH, which is the negative log of 0.1, that equals 1. Okay? I did that fast because this is a skill. Once you understand what's going on here, you should be able to look at anything that's a strong acid or a base, and you can directly calculate what the pH is by taking the negative log of that. For this reason, everything that you start with is going to end up in products. But now we've got a weak, and we can't play that game anymore. Now we've got a weak acid. Here's the molecular reaction. Okay? Here's the Ka for acetic acid. What's the pH? How are you going to figure that out? Why don't you guys discuss how you might approach that? I'm not going to tell you yet.
Tell them, Catherine.
Tell them.
It's a rice table.
Yep.
Don't ask, what does that mean? Okay. Yeah, it's a rice table. Use a rice table. What's the change going to be?
It's going to be minus x on the left.
It's going to be minus x on the left,
Plus x
plus x and plus x, because this equation is balanced, right? If there were coefficients, then those coefficients would come down to modify the x's. But it's all 1 to 1 to 1. So what's the equilibrium concentration going to be for acetic acid? I shouldn't have written it down. Right? That's the molarity. And the acetate ion, that's what this is. Acetate ion is going to be what? X molar. And the hydronium ion will also be X molar. How come I don't have anything written under the water? Because why? I can't hear you. Because the concentrations aren't changing throughout all of this. The concentration of water stays the same. And even if you didn't understand that, right, these are really, really super dilute solutions. It's mostly water. So even if the water concentration did change, it's insignificant. But it doesn't matter because the concentration of water isn't changing. So no change. So we can build our equilibrium expression because we know that that Ka is equal to the concentration of, and do I have to write all of this in? Do you know what A minus is in this reaction? What's A minus?
CH3COO.
It's the acetate ion. That's A minus. This is our H plus, and this is our HA. Okay? So we know that this is equal to H plus multiplied by A minus, multiplied concentration, multiplied by the concentration of HA. And we know what all those are now. So let's plug all that in. All right, that's going to be H plus is X, and A minus is X, and HA is 0.1 minus X, and all of that's going to equal 1.8 times 10 to the minus fifth. So now what are we going to do? You want to use the quadratic formula?
Not preferably.
This is X squared, right? Do we use the quadratic formula? Is there any way around using the quadratic formula that we talked about in chapter 14? Say that louder. Ka is so small that tells you that the extent of this reaction is very, very small. It's mostly going in this direction, not that much in this direction. So whatever X is, it's going to be so small that when you subtract it from 0.1, it's pretty much still going to be 0.1. You can ignore it. Negligible because KEQ is so small. And our rule of thumb here is we want to be, what did I tell you the last time? 10 to the negative 3 or 10 to the negative 4? 10 to the negative 3. Let's hope that you never get a problem that gets you right smack dab in the middle of the gray area. But you know, if you had to do the quadratic formula, it's not so bad. I made you do it once or twice. You know, it might not hurt to practice it once or twice, maybe not for my class, but maybe for some future class or exam that you take. But it might also be good to recognize when you don't have to do it. All right, so it's so small we can ignore it. So now this simply becomes x squared over 0.1. And that's easy. That means that x squared is equal to 1.8 times 10 to the minus 6. I just multiplied that by 0.1. Okay? And that's actually easy to do in your head, right? X is going to be equal to something times, what's the exponent going to be? What's the square root of 10 to the minus 6? Oh, come on, you guys. When you multiply them, you add the exponents. When you divide them, you subtract the exponents. So this is 10 to the minus 3. What's the square root of 1.8? That's a little harder. You know what? Just use your calculator. 0.00134. Is that what you got? So that's what x is, just making this assumption that it's negligible here. But look at, if we did it by the quadratic, we'd get a slightly different number. But we're still, when we subtract that from 0.1, we're still going to get 0.1. Down to 0.10 something. So we're good. Now that's X. We want to know, what do we want? We want to know the pH. So that's X, that's this right here. So what's the pH? Negative log of what? What's the hydrogen ion concentration? What's the hydronium ion concentration? It's that number, 0.00134. So what's the pH? Just take the log of it in your calculator and then reverse the sign in your head, 2.87. Now, if that seemed complicated to you, just review what you've learned with me this semester so far, because this is absolutely no different from what you studied in Chapter 14. The only addition was doing that final log transformation, because that's pH. All right, you guys try this one on your own now. I'm giving you a 3 molar aqueous solution of ammonia. Here's the Kb. Calculate the pH. You need me to give you that equation? All right, fine.
You don't mind.
I do mind. NH3, an aqueous solution, as a base in H2O, in equilibrium with, what's the conjugate acid of ammonia base? If you can't figure it out, just add a hydrogen. All right, that was a neutral. We added a hydrogen ion. So it's NH4 plus, aqueous solution, plus OH minus in aqueous solution. I'm going to do it along with you. So if you don't want to see how it's done, don't look at the screen. Okay. Is this the right answer?
No,
It's not the right answer.
you gotta subtract it from 14.
Got to subtract it from 14 because we're working with the base. One of the most common errors students make is that they do all this stuff and they say, okay, here's my answer, okay, without recognizing what it is they're doing. We're working from a base. Don't be that student, okay? This is a base. All I did was calculate the negative log. That's the POH. So the pH is going to be 14 minus 2.14, which would be, what is that, 11.86?
Yes.
That's the pH. And as a mental note, okay, when you're working any of these acid-base problems, if you put an acid in water, you expect the pH to be less than 7. If you put a base in water, you expect that the pH will be greater than 7. And if your calculator tells you something different, then you either entered it in the calculator wrong or you didn't realize what you were working on. Okay? So it's a good check and balance as you're doing this stuff. This is actually a slide that I teach in Gen Chem 1 as well. It just reminds you of the different kinds of acids and bases that we have with respect to now how many moles of hydrogen ions or hydroxide ions are produced for every mole of the acid or base that you put in there. We've been working so far with just monoproduct, although that's not true. In lab, you used the diproduct acid, didn't you? You used sulfuric acid, and that threw everybody for a loop. But the only difference there with sulfuric acid, which is listed right here, okay, is it produces 2 moles of hydrogen ion for every mole of acid that you have in solution. And I'll just start with sulfuric acid. You know, that's also a strong acid, okay? But with these diproduct and polyproduct acids, they don't lose all of those protons at the same time. Each one of them is lost at a different Ka. For example, in sulfuric acid, we know that the first dissociation is strong. It's 100%. In fact, that's why we call it a strong acid. But sulfuric acid, as a strong acid by itself in solution, has really only lost 1 proton. The products are the hydronium ion over here and this thing, which we call the hydrogen sulfate ion. And notice that sulfuric acid, that's a neutral. Hydrogen sulfate ion, that's a 1 minus. Now in the titration experiment, you actually lost both of the protons because you kept adding sodium hydroxide. This is just sulfuric acid and water. If we had sodium hydroxide in here, you've constantly adding hydroxide ion that's reacting with this one. So it's taking this out of solution. All right. So by Le Chatelier's principle, more of it dissociates, and that keeps happening until you finally neutralized all of the hydrogen ions. But you've never really gone all the way over to here until the end. There is, if we just had this in solution, hydrogen sulfate ion, this is also a weak acid. There is a Ka here for this. It's about, it's sort of weak. It's I have it written down here. The Ka is 1.2 times 10 to the minus second. And to be more specific here, okay, that Ka, so Ka, I'll call that Ka2, because it's Ka for the second dissociation. That's going to be equal to the concentration of the products, which is hydronium ion, times the sulfate polyatomic ion, divided by the concentration of the hydrogen sulfate ion. Because now this is the acid. Here's carbonic acid. You might not have seen carbonic acid before, but it saves your life every day. It's saving your life right now. It's really important in the blood chemistry. I think I talked about it a little bit in the introduction video. It's a diproduct acid. Every 1 mole of carbonic acid can produce 2 moles of hydrogen ion in solution, but it does it sequentially. There's 1 Ka, and these are both weak. The first Ka is on the order of 4.3 times 10 to the minus 7th, so it's a pretty weak acid. And that just produces hydronium ion, and we could call it the hydrogen carbonate ion, but you know it as, this is the bicarbonate ion. Okay? And then that has a hydrogen on it, and that hydrogen is also acidic, but it's even weaker. There's another Ka, Ka2, which is even weaker than that. That's 4.8 times 10 to the minus 11th. So they're lost sequentially, and each one that's being lost, it's weaker and weaker and weaker.
KB will be getting greater.
Here's phosphoric acid. I won't list everything here, but that has 3 moles of hydrogen ions that can be donated to solution, and each one is lost sequentially, and each dissociation is dominated by its own equilibrium constant, and each one becomes weaker and weaker as you dissociate more and more of them. Well, let's take a look at sulfuric acid. All right, I want to emphasize this learning outcome right here. And we're going to do this problem from the textbook. We're going to take 0.1 molar sulfuric acid, and we're going to calculate what the pH is. Just like we did in previous lectures where we did the pH of 0.1 molar HCl, and we know how to do that because HCl is a strong acid. So we know that this goes 100%, and so it's going to be 0.1 molar H+, and we can calculate the pH of that. And then I showed you a problem where we can do that for a weak acid. We did 0.1 molar acetic acid. And that one is in equilibrium, right? So we built a rice table, and we were able to figure out what the pH of that was. Now we're going to do it for a polyproduct acid, all right? And we're going to see what the pH is, and you'll see how these different Kas play a role here. So we can keep this in here. Just reminds you of the comparison. Well, first let's put the equation up here, all right? And let's treat these what I call deprotonizations or deprotonations, or the loss of the first hydrogen ion. All right, that's going to look like this: H2SO4 in aqueous solution. The first one is lost 100%, so I'm going to have a solid arrow going to the right, and that's going to give us hydrogen ions in aqueous solution plus the hydrogen sulfate ion in aqueous solution. And we don't need a rice table for this one because it goes to completion. So we can just say initially we started with 0.1 molar and we have 0 molar here and 0 molar here. So what's it going to look like final? What's the concentration of sulfuric acid going to be?
0.1.
It's going to be 0. Sulfuric acid, 0 molar. And for the hydrogen ion concentration, that's going to be 0.1 because we know that it goes completely. Okay? And that's it for the first. But we know that there's a second reaction that's also going to contribute to the pH. If we stopped here, we know what the pH would be. What would the pH be without calculating it? Can you tell? If we stopped right here, it would be 1. Because this is 10 to the minus first, and the negative log of that is 1. But we're not stopping there. We know that there's another reaction. So now we need a rice table for that one. So let's do the second reaction. That's going to be hydrogen sulfate ion in aqueous solution is going to be in equilibrium with a hydrogen ion in aqueous solution plus the sulfate polyatomic ion in aqueous solution. Now, before we go any further, let's just do a thought process. We know that for sulfuric acid, if only one proton comes off, then we know that the pH is going to be, then we know that the hydrogen ion concentration is 0.1 molar and the pH equals 1. What would it be if both of them came off? If both hydrogens came off, what would the pH be? Let's just play a little game. Look up here in blue. All right? 0.1 molar sulfuric acid. 1 mole of sulfuric acid produces 2 moles of hydrogen ions. So if that's true, if all 2 moles of hydrogen ions went off into solution, what would the concentration of hydronium ion be? The concentration of this would be 0.2 molar. What would the pH be? It's not 2. Aha. That one you might want your calculator for. You need the negative log of 0.2. 0.7. Yeah, you were going to say 0.69, but that's okay. So we know that if the first mole of hydrogen ions that come off would give us a pH of 1. If both of them came off, we have a pH of 0.7. But we know that the second step is weak, so we're not going to get all 2 moles of protons dissociating into the solution. So we would expect our final answer to be somewhere between 1 and 0.7 if we calculate the pH of this. Agreed? Okay, so keep that in mind. Better make sure that we end up there. All right, so now we need a rice table for this second one because this is now hydrogen sulfate ion is a weak acid. So here's the R for our rice table. What's the initial concentration of hydrogen sulfate? 0.1, because we just made it, molar. What's the initial concentration of hydronium ion? 0.1. And this is 0 molar. Now we need the change. Now, do we need to calculate Q first? And we know what KEQ is. I just didn't remind you of it. KEQ is written right up here. 1.2 times 10 to the minus second. So let's write that back down here. So Ka 2 is going to be 1.2 times 10 to the minus second. We don't need to calculate Q first because one of the products is 0, so we know that the reaction is going to go in the forward direction. So what's the change going to be for hydrogen sulfate ion? Minus X, and this is plus X, and this is plus X. So at equilibrium, we're going to have 0.1 minus X for hydrogen sulfate, 0.1 plus X for hydrogen ion, and X for sulfate ion. Now we can build our equilibrium expression. We know how to do this. This is good review. KEQ is 1.2 times 10 to the minus second. That's equal to the products 0.1 plus X times X divided by the reactants 0.1 minus X. Okay? Now, if we were to work this through, I mean, this does become a quadratic. You'd have to solve for the quadratic, right? And I don't want to spend more time doing that. I keep reminding you, you should be able to do it, okay? If you go ahead and solve for X, I'll just tell you, because this is really more of just a demonstration. If we solve for X using the quadratic formula, it should be 0.00985 molar. Okay? So that means that if we want to know what the final hydrogen ion concentration is going to be, we need to add that to 0.1. So this plus 0.1 is equal to 0.10985, and the negative log for that, pH is equal to the negative log of 0. I'll just round that to 110. Okay? Sorry, 0.96. Does that make sense? So it is between those two numbers, but it's very, very close to 1. It's much closer to what we get from losing the first mole of H plus than it is if we lose both of them. Part of this learning outcome is not just to recognize that the Ka gets weaker and weaker, but also that what it says right here. It's typically only the first deprotonation is what significantly affects the pH. It's really just the highest Ka, the first one, that affects it. All the other ones are, because they're progressively weaker and weaker, and because this is a log base 10 scale, all right, this is also really, really important. Even though we just spent a little bit of time to actually do the math, you can look at this, and if you were given, say, multiple choice, if you were like taking a standardized test, not mine, my tests aren't standardized, but if you were taking a general standardized test and you were given something like sulfuric acid and the answer choices for pH is far enough apart, you can just figure out, well, I know the first one's strong, and I know how to do that pH, and I also know that there is a second one, but it's weaker, and in fact, it doesn't really significantly affect the overall pH. I'm going to just go with the first one because you understand this principle. You know, when you look at this expression, and I told you, well, it's a quadratic, so you got to do the quadratic formula. And you might say, well, wait, can't we use one of those shortcuts? So like X is negligible or whatever. And you might say, well, no, you can't, because I told you can't do that unless this is like 10 to the minus 3 or lower than that. But you know what? You might want to just try that for fun. Try to reduce this. If X was negligible, and we ignored that X and we ignored that X, look what happens. X is equal, here, let's put it here. If X is instead equal to 0.012 plus 0.1, that equals 0.112. So what's the pH of that? 0.95. So it is different, but not by a lot. Okay? So I point this out because the rules, these aren't rules, they're just guidelines. When can you make this assumption? When can you not make this assumption? All right? This is just showing you, right? In green is when you don't make that assumption, and so you solve the quadratic and you get this for x. And in blue is where you do make that assumption for x. Okay, so let's have a discussion about titration curves, and now put this into context with the conjugates that we discussed. So on the left is the kind of titration curve that you generated in lab last week. That's when we had a strong acid reacting with a strong base. This week in lab, we're also going to be looking at a weak acid with a strong base. And you can already see that the shape of the curves are a little bit different. All right? I'm not going to talk too much about that right now because you're going to be exploring that in lab tomorrow. But I do want to talk about the reactions and what happens at the equivalence point and what's left over at the equivalence point. So I'll remind you that for any of these reactions, and it doesn't matter what they are, I'll just put a generic strong acid and a generic strong base, right? And we know what products that's going to create. Actually, let's go ahead and put them in. What would the products be here? It's strong. What are the products? Acid and a base. You get water and what else? And a salt, right? A salt and water. Now in this case, the salt happens to be table salt because of the one that I chose. NaCl plus H2O. And here, let's do the weak acid. Let's use acetic acid for our weak acid. And we'll still use sodium hydroxide. So what's the salt going to be?
Ch3CO.
CH3COO. What do we call that? Yes, it's the acetate ion, right here. See, where is it? Here it is. Right? This is the acetate ion. It is reversible. If it's a weak acid, it's reversible, and that's exactly what we're going to be talking about. So, but I have an arrow, I have a solid arrow going to the right, because even though acetic acid is reversible, this reaction, so this is sodium acetate plus H2O liquid. Even though the acetic acid is in equilibrium with the acetate ion and hydronium ion, we're adding sodium hydroxide. So via Le Chatelier's principle, we're constantly pulling the acetic acid into its component ions through the neutralization reaction. So ultimately, this still all goes to product in the end. But ultimately, even though these look complicated, without me having to write out the full ionic equation and cross things out and everything and end up with the net ionic, what is the net ionic equation of both of these? Always. H plus OH minus goes to H2O. That's what's at the heart of both of these. That's your net ionic equation of any acid-base neutralization reaction. Okay? So what we learned last week, right, at the equivalence point, what's equal at the equivalence point? The concentration of H plus and OH minus, right? Here, now I'll remind you, that's the same, that's the hydronium ion concentration is equal to the hydroxide ion concentration. If we do this very carefully in a titration experiment, drop by drop, when you get to that magic point, okay, especially when you graph it on a curve and you extrapolate the equivalence point, because we also learned that the endpoint is out here. The endpoint is when the color changes. The equivalence point is this part of the curve. But what you hopefully learned in lab last week is that we can use the color change of the endpoint to approximate the volume that it takes to get to this equivalence point. That, if you didn't realize that, that was one of the learning outcomes. All right, but at this equivalence point here, okay, if we've done things carefully, there's no more hydrogen ion in solution, there's no more hydroxide ion solution. They've all merged to form H2O. So what's left? What's left over? Here, let's write this down. What's left over at the equivalence point? What do you think? Is there hydrogen ion left over at the equivalence point? Is there hydroxide ion left over? What's left over? So at the equivalence point, right, all of this has reacted with all of that to give water. So what's left over? Well, the water's there, but the ions, what ions are left over? Yes, the water's there. Yes, that's true. What else? I'm sorry? The sodium and the chloride, right? We've been ignoring them. We've been shaming them by calling them spectators, okay? But they're actually what's left over at the equivalence point. The spectator ions, all right? In fact, by definition, that's what you would expect of spectators. They weren't involved in the reaction. The reaction, we got it down to the drop, right? So the reaction has gone completely stoichiometric. Nothing's in excess, nothing's limiting. It all went 1-to-1. So yeah, we made the water, and what's left are these spectator ions. They're still floating around in solution. So what are the spectator ions in the acetic acid sodium hydroxide reaction? What are those spectators? What's left over at the equivalence point? Sodium and acetate. That's right. That's what's left over. So now the question becomes, what effect do those ions have on the solution when we're at the equivalence point? It's an interesting problem. Take a look at sodium ion and the chloride ion. Where did they come from, right? What are they on this conjugate chart? Here's the chloride ion, and you might recognize that chloride is the conjugate base of HCl, and HCl is a strong acid. So remember that conversation that we had last Friday. If it's a strong acid, HCl goes 100% into H plus Cl minus. So even though we call this a conjugate base, does it really behave like a base in solution? Does it actually act as a base and accept that proton in solution and form HCl? No. We call it a conjugate base, but it's of negligible strength. So it doesn't really happen, which means it's not having any effect on the pH. If it did happen, it would combine with the H+, take it out of the solution, and that would give us more of an acidic pH because we're lowering the hydrogen ion concentration. The same argument goes down here for sodium hydroxide. Now, hydroxide is a strong base. Now, where did the sodium come from? The sodium came from the sodium hydroxide. Okay? So when we have this strong base, we form sodium plus ions and hydroxide ions. It's really the hydroxide ions are actually the base. Sodium is the spectator ion that came along for the ride. But we call this the conjugate acid of the strong base. Does it really act like an acid? No, it doesn't. It's of negligible strength. So it's not going to have any effect on the pH. So if we look down here, right, this is the conjugate acid of a strong base, and chloride is the conjugate base of a strong acid. Both of these are negligible. Meaning they have no effect on the pH. And if the hydronium ion is the same as the hydroxide ion, we already know that's going to give us a pH of 7. And the conjugates have no effect on the pH, so overall we expect the pH to be 7. And in fact, it is. Or at least you should have gotten very, very close. So we expect then that the pH at the equivalence point should be neutral. All right, let's look at it on the acetic acid side. All right, sodium ion this again is, let's keep my color scheme the same. This is the conjugate acid of a strong base. Right? That has negligible strength. But what about the acetate ion? What is it? It's the conjugate base of a weak acid. Here it is. Okay. Acetate ion is the conjugate base of a weak acid. Meaning, is it a conjugate base? Is it a strong base then? Is it a weak base, or is it a base of negligible strength? Remember, the conjugates of a weak are also weak. So acetic acid acts as a weak acid that forms the acetate ion as a conjugate base, but that's a weak conjugate base. Meaning that, where should I put that? Let's put it here. Meaning that the acetate ion behaves as a weak base. There's the acetate ion in aqueous solution plus H2O. Will go back and it will form acetic acid. And in the process, we'll have OH minus. That's the main reason we spent so much time looking at conjugates on Friday's lecture. If you have a strong acid, the conjugate base is of negligible strength. If you have a strong base, the conjugate acid is of negligible strength. But if you have a weak acid, the conjugate base of that weak acid is itself a weak base, and vice versa. And that's going to have an effect on the pH at the equivalence point. And you can see that right here, all right? The sodium ion is not going to have any effect, but the acetate ion does. And the acetate ion will behave as a weak base, so we expect the pH at the equivalence point to be basic. And if you look here at the equivalence point and extrapolate it over, sure enough, it's in the basic range. But these are the spectator ions, okay? The spectator ions are actually now no longer going to be spectators. They were spectators watching the main reaction happen, and once that all got neutralized, now if they are weak acids or bases, they are going to undergo a reaction with H2O to make it either more acidic or more basic. Those rules again, let's just do it with some practice problems. And I'll just start you off with the first one to remind you of what the thought process is here. Here's ammonium bromide. Okay. It's not an acid or a base, but it is a strong electrolyte. All of these will be strong electrolytes. We're not challenging you on that yet. But that, as an ionic compound, when it breaks apart in aqueous solution, what are the ions? What's the cation? NH4 plus. That's the ammonium ion. And then the anion is what? The bromide ion. Now, how are we going to evaluate? What effect will that have? What effect will those ions have on an aqueous solution? We're just putting this in water. So to answer that, you just see, well, how would this react with water? We know that the cation is going to associate with the hydroxide ion, right? How does it react with water? Here, let's just put this up here. How does it react with water? That will tell you whether it's going to be a conjugate of a strong acid or base or a weak acid or base. The ammonium ion, well, that's going to associate with hydroxide ions, and the bromide anion is going to associate with hydrogen ions. And now, ask yourself, is HBr, is that a strong acid or a weak acid?
Strong.
It's strong, right? You only have to know the 6 strong acids, and this is one of them. So this is a strong acid. that means that the conjugate base is bromide minus, and the conjugate base of a strong acid is that strong base, a weak base, or base of negligible strength. It's negligible strength. Where does the ammonium ion come from in the reactions we've been looking at? NH3, ammonia. I should do that in blue. NH3 plus water gives you the ammonium ion plus OH minus. It's in equilibrium. So you should already recognize this as the conjugate acid of a base. And it's in equilibrium, so they're both weak. This is a weak base. This is a weak conjugate acid. In the context of looking at it, how it reacts with water, the strong bases are group 1 and group 2 metal oxides and metal hydroxides. And those are considered to be strong bases. Everything else you can consider to be a weak base. This is the conjugate of a weak base, meaning that it is a weak acid. So in solution, we have a negligible base and a weak acid. So what's the pH range going to be when we put ammonium bromide in aqueous solution? Is it going to be acidic, basic, or neutral? It's going to be acidic. Now, you do the same with some of these. Actually, you do the same with all of these. To establish, overall, is it going to be acidic, basic, or neutral? So go ahead and work in your groups. Acid of what? All right, let's start working through them. You might not be done, but I want to make sure that you understand the thought process, because once you get them, you'll be able to do any of these, okay? The logic process is all the same as what I just showed you here. So here, I'll just switch colors so that we can keep things neat. All right, so here's some sodium carbonate. So let's just look at the ions that are formed. All right, we've got sodium cations and we have carbonate anions. What is sodium the conjugate of if we mixed it with water? What effect would it have on the water? It wouldn't take a hydrogen. Right? This is a cation. The cations are going to be associated with the hydroxide ion. Okay, so just split the water up and then stick it to the appropriate ion. Right? That would form sodium hydroxide. Is sodium hydroxide a strong base or a weak base? It's a strong base, which means that this is going to be a negligible conjugate acid. Is that going to have any effect on the pH of the water? No. How about the carbonate ion? What are we going to add to the carbonate ion to figure out what acid it came from? Stick protons on there. What does that give you? H2CO3, carbonic acid. Is carbonic acid a strong acid or a weak acid? It's a weak acid. That means that the carbonate is going to be a weak conjugate base. What effect will that have on the pH of the solution?
Increase the pH.
It'll increase the pH. It'll make it basic, right? So the sodium doesn't do anything. The carbonate ion makes it basic. So this is overall going to be a basic pH if we put that salt. There's no acids or bases here, okay? If we put that salt in water and put a pH meter in there, it should have a basic pH. That's all we're doing here. All right? Is that iron 3 nitrate or iron 2 nitrate?
Iron 2 nitrate.
Iron 2 nitrate. So that's going to give us iron 2 plus, and nitrate ions. When we stick the iron 2 plus with OH minus, what does that give us? Iron 2 hydroxide. Is that a strong base or a weak base? How do you know it's weak?
Because it's a transition metal.
Because it's a transition metal. It's not a group 1 or group 2 metal. Okay? So this is a weak base, meaning that this is going to be the conjugate acid of a weak base. It's going to be weak. So that will turn the pH acidic, but let's take a look at what the nitrate ion is. Where does the nitrate ion come from if we react it with water? HNO3. What is that? Nitric acid. Is that a strong acid or a weak acid? It's a strong acid, which means this is a negligible base. It's the negligible conjugate base of a strong acid. So when we put iron 2 nitrate in aqueous solution, so this should be acidic. All right, calcium sulfate. Calcium ions, 2 plus. Where do they come from, or what would they react with when we put it in water?
CaOH.
CaOH2. Calcium hydroxide. Is that a strong base or a weak base?
Strong.
Strong base, which means this is a negligible acid. And then we have the sulfate ion. What would you get? What acid would that come from if you put hydrogen ions on there? Sulfuric acid. Is that a strong acid or a weak acid? Strong. Which means that this is a negligible base. Negligible conjugate base of a strong acid. So what effect would that salt have when you dissolved it in water? What would the pH be?
Neutral.
It would be neutral. That's right. Because neither of them are having an effect on the pH now. So this one's neutral. Very good. Sodium ions. This is sodium hyperchloride. For those of you who don't remember your oxo halogen, whatever they're called, sodium hypochlorite. So the sodium ion, we already know that's going to be weak, negligible. This is a negligible acid. And the hypochlorite ion, that would be ClO minus. How do we evaluate whether that's an acid, or what kind of acid it is? We stick a hydrogen on it. All right, so this is going to be a weak acid, which means that this is going to be a weak conjugate base. So the pH of the solution should be basic. And that's how you do these. So yeah, you can get an acidic or basic solution even if you don't add an acid or a base. You're just adding salts, but the salts are the conjugates of acids and bases, and now you know how to evaluate that.